Okay, my presentation will be a bit different than the previous works presented here. Here I will introduce our new testbed for distributed communication, sensing, and positioning. As it's there in the title, it's a primer because it's still a work in progress. A spoiler is behind me. I'm inside the testbed. Why do we need this new testbed? It's to evaluate the radio weaves concept. In the radio weaves concept, we're moving from a central antenna or a base station, which is very high on top of buildings to serve multiple users, to actually embedding electronics and antennas and other sensing and sensors and electrical equipment inside walls, buildings, and objects which surround the users which needs to be served. So previously, if the base stations are on top, and if you're looking at 5G, what is done is that the energy is beamformed towards the users, creating these beams, if there is a line of sight, beams towards the user. If we are, however, in a radio weaves infrastructure, we are very close to the antennas, which result that users are in a near field, which is a good thing in this case, because the beams are no longer beamformed towards the user, but are actually concentrated, or the energy is concentrated very close in a radius very close of the user. There are more benefits which you could read in our paper and in the paper which is below the presentation. But to evaluate this radio weaves concept, we have some questions. How can we implement such a thing where everything is embedded in the walls and in the things which surround us? How to connect these different electronics? How to coordinate? Do we need to process locally? Do we cluster some of these antenna elements? How dense do we need these radiating elements? If you have a restriction in the number of elements you have, if you make them less dense, you can cover a larger area, for instance, a surface of a building or something, and then we need to deviate maybe from what is normally done with multiple antenna systems. There we place antennas which are spaced lambda over 2, which is equivalent to the Nyquist criterion, which you all know from DSP applications. So this requires new models, architectures, topologies, protocols, processing, signaling, multiple access techniques, and this is done, or hopefully will be done, in this tactile infrastructure. This is a part of the team, which you could see here. There is me in this tactile infrastructure. I'll be using this figure to show and to touch upon the different things which is the tactile infrastructure. As you could see here, this is a plan of the tactile infrastructure. We have, hopefully you will see my mouse, we have some tiles here, and we have the whole infrastructure, and on each of these tiles we have an edge device able to compute stuff, sensing, radio, where you can control, it gets power and so on. Everything which is designed in this tactile infrastructure, in this testbed, you can see on our GitHub, CNC stuff, 3D printing, source code, PCB design, whatever is available here on GitHub, and also on our website for a more human-friendly approach. To go to the construction, it is modular and open. It's based on the wiki house concept, which you can see here on the bottom, which is quite convenient to install and to modify. The room is by itself 4 by 8 meters and has a height of 2 meters. 0.4, and it consists of 140 of these tiles. That also means that we have 140 of these end devices which are equipped or which are attached to these tiles. I'll come back to that later on. So how, me again, there you could see at the right the tile with some of the default setup, which I will discuss later on. Such a tile is 60 centimeters by 120 20 centimeters and consists of or has a grid where you have 5 by 5 centimeters where you can plug in and screw in electronics, which you can embed in the background of this infrastructure. So the electronics are obfuscated, they're embedded in the infrastructure. So you're able also to design your own tile if you have certain restrictions. So for visible light, communication and positioning systems, there it could be useful that you design your own tiles with your own LEDs. We also allow to attach things to the inside of the room by using overlays. There you can just add an overlay on top of such a tile, and then you can mount temporarily some of these equipment inside of the room. But as we want to evaluate the radio waves concept where we have all these things around us and embedded in these infrastructures, we actually if you could put your electronics inside of the building, this would be better. But some things require line of sight connections or temporarily studies to know where to place certain stuff. There we allow to have an overlay inside, and there you can design your own stuff as well. To the backbone, everything is connected over Ethernet. Because we have this giant infrastructure, or relatively giant, and we have a lot of electronics, these need to be connected, and to be able to be scalable, we chose for Ethernet. Ethernet for power, Ethernet for control signals, for data, for timing, for everything. That's why we use the term everything over Ethernet. So at the backbone, it consists of two separate systems. First, we have the data acquisitioning system where we can sense stuff. And then at the right, we have our server infrastructure, or an overview, where we have a time provider, which I will discuss a bit later. We have our power over Ethernet midspans, providing power to all these 140 units or tiles. We have some DEL switches, which are capable of this timing synchronization. And we have the central server with a lot of RAM, GPUs, CPUs, which can handle some CPU or processing stuff. So the data acquisitioning system, there we have 1.5 mega samples per second, which we can acquire with a resolution of 60 bits. And we have 192 channels, which means we could have multiple electronic sensing stuff you need to acquire on one tile. So we have a bit more than required. Okay, so coming back to the server side, so over the power over Ethernet midspans, they inject 90 watt power per port. So that's the maximum we support. And then I'll have a quick introduction and elaborate more on the time provider, which protocol we use for synchronizing all these tiles. Because if you're using this infrastructure, you want that all these tiles have the same global clock. So here we use IEEE 1588 versus 2, or better known as the Precision Time Protocol. It's very similar to Network Time Protocol, which you all use on your computers, if you want to or not, to have a time synchronization. So how does Ptp works? One of the mechanisms to determine a clock based on a master is end-to-end delay mechanism. There the master sends a sync message, and depending on the capabilities of the master, this sync message already includes the first timestamp, which is provided if the master supports hardware timestamping, because then on the network interface, the timestamping is set. Otherwise, there is a follow-up message containing this T1, this timestamp 2. The slave receives the sync message on T2, and then later on can acquire T1. Then it knows the time at T1 of the master, and then it does a delay request and gets a delay response to know the delay on the network between the master and the slave. Here I denoted what the master and this is an indication of a master and a slave, where you could see there are some stuff in between the master and the slave. And because of the collected timestamps, you could easily do the math. You can compute the offset to correct your time, the slave, to the master. There is another mechanism, peer-to-peer delay mechanism, which where we do not correct immediately the time between the master and the slave, but we first we acquire the network delay on the links rather than end-to-end between the two nodes. And there, one of the two, clock A is, for instance, this node, and clock B is this node, and there they just compute the network delay. And then the slave can just use the master time plus the network delay and compute its offset. But the master still needs to provide a sync message to know what the time is at the master. And then this middle node, if these are back the master and slave, this middle node can remove the delay of the links between these two of the sync message. So the slave, the sync message received by the slave, it looks like there is no network delay anymore, improving the accuracy of the PTP mechanism. By using this mechanism, peer delays are already known at the time of sending the synchronization message between the master and the slave. And we only need the synchronization message, while in the previous mechanism, there was also this delay request and response. And this delay request response could follow another path and thereby could have another network delay, having an impact on the performance of the PTP accuracy. This also results in less load for the master clock, because otherwise the master clock needs to communicate with all these slaves through a delay request and delay response, while now it's between different clocks. So all these things together allow the PTP protocol to achieve an accuracy close to sub-nanosecond synchronization. So to summarize a bit what PTP does, as it removes the delay in the stack because of hardware timestamping, no software is involved. We can remove the delay on the network because of this peer-to-peer mechanism. And we can remove delays inside the switches if the switches are capable of being a transparent clock, removing these delays. Going back to the tiles, we have, so as you could see here, we have some sensing capabilities, some radio acoustic, VLP, we have our controller here, but in the default setup, we focused on the radio. Here we have the national instruments, USRP, which is a software-defined radio, and as an edge computing or controller, we have a Raspberry Pi 4 equipped with a SSD instead of a micro SD card, because it's more robust to power failure. The write and read speeds are much higher, and we have more capacity as well for the same price. Then for the power, we need to power. As I said, everything is over Ethernet. So we have power over Ethernet, where a colleague designed this PCB port, this power over Ethernet port, where the data is coming in from the network, and the power is injected, or the power injected from the network is here outputted over different connections. So we have a USB-C cable specifically for the Raspberry Pi. We have some 5-volt outputs with a USB-A connector, C connector, some terminal blocks. We also provide the 48 volts, which is coming from the power over Ethernet itself. It uses 48 volts, which you can use, or you can have an optional converter deployed there to have a voltage which you would like for your application. At the radio side, what is a software-defined radio? Just a small introduction. There we use baseband signals. it's your signal, which is not up converted to the RF part. So this is done with your Raspberry Pi, a controller. There you design your waveform, your baseband signal, and over USB you transport that to the USRP, which you could see here. And this data is up converted, is moved from the analog domain, from the digital domain to the analog domain, and is transmitted. And we have the other way around when receiving. By using the software-defined radio, you could quickly build different systems. You could build upon existing solutions. So, for instance, this USRP supports GNU Radio, LabVIEW for the guys and girls who like to work in a MATLAB environment, or you could use their own driver to have a low-level interaction with the device. To a few of the possibilities in GNU Radio, there are some protocols already implemented by the open source community. So, for instance, Bluetooth, Wi-Fi, 15.4, which is very much used, and even LTE. So the possibilities are endless, or almost endless. And able to use this setup in this radio weave kind of concept, we need coherent operation. So we need that each of these USRPs, these software-defined radio, act as if they're one system. To do that, we need time synchronization. So we have this time synchronization over Ptp, which we acquire here in the Raspberry Pi. And we made a PCB outputting a 10 megahertz clock and a PPS, which is synchronized over all these tiles, which are used in these USRPs to have a coherent operation. Which you could see here. Here are two Pis, and here we're looking with a scope to see what accuracy we could get. As said, it's still under construction. We were close to tens of nanoseconds, but we're still working on it to achieve even better accuracy. We also have a robot, a rover or a robot in place where we could do automatic sampling of the room in 3D space, which resolves some issues with human errors, as well as it being very labor intensive. So we have at the left a scissor lift, which allows us to elevate certain measurement equipment, and there we have a range between 55 centimeters, 185 centimeters, which is put on top of this base plate, which uses a MarvelMind setup, which uses acoustic waves to determine the position of the rover. We have a battery pack powering the rover, powering the scissor lift, and powering the equipment which you put on top of these scissor lift. It works on a robot operating system. It uses Kalman filtering to filter out outliers, and it also has some minor object detection to avoid collisions. What we foresee as research activities, it's not an exhaustive list, is things concerning Internet of Things, beyond 5G communication, acoustic sensing and indoor positioning, wireless charging, and visible light communication and positioning. To just pick one topic or activity, a colleague of mine has been using this testbed to estimate the position based on acoustic waves in combination with our RF. I've put a reference below, and you can always contact him for questions on how it works. Of course, we're very interested for you guys. It's not only us who are going to use this tactile infrastructure, so we invite you for creative experiments. A bit of a conclusion. So this is our tactile infrastructure. You can have all this information, or you can find all this information on GitHub and on our website. If you click on our website, you land on this page. Please subscribe, and then we will send out newsletters concerning how we are doing in this testbed. I've also put some of the companies we've worked with or gave us some equipment as a thank you note. And to conclude, we just installed the seat and our new coffee machine. If I didn't persuade you to use our infrastructure, maybe this will. Thank you.